EET 118 Lab AC3 Experimental Determination of Capacitor and Inductor Values. So basically, we're going to go through here and empirically and calculate the capacitance in an RC network and also the inductance in an RL network. We're going to use an oscilloscope or with every circuit, and we're going to have to do a lot of time constant calculations. So we're going to set up these resistors, this capacitor. I'm going to do part one for you, and you guys are going to end up having to do part two in the exercises. Um, Basically, the resume of theory talks about the time constant and these equations here and how they relate, and you can actually calculate the capacitance and the inductance using these equations. So in here, in Excel, I this is a formal lab, and I put the cover page on here. It looks like this. If you look at the print preview, this is what it looks like. It's not exactly centered, but I can fix that. Okay, so I fixed that. And then if you have a partner, which you guys are not going to have if you're online, but if you're in actually in the lab, you will have a partner. So you put both partners' names there. And at the top of every page, I want a summary of what exactly this report is. So here's what that that looks like. It's going to have the report, your name, the course name on it, just something like that. It's as long as it identifies those three things. The objectives are these. This comes straight out of the lab assignment. I just type these in directly. Okay, right here are the objectives, and then the equipment required and issued, and then the theory. So the equipment required is here. I put a nice little picture um, of a piece of equipment that came out of the book. The theory basically is just a rehash of the theory that was spelled out in the lab. Here's the theory that was in the lab, and it ends right here. One important point here, I put a background, and this is chosen at the discretion of the student, meaning that what you say here, it needs to relate in some way to the topic of the lab. So I put a note in there on that. You do not have to do the lab in Excel. You can do it in Word as long as, like I said, it's clear and neat. You could do it in either or. I kind of prefer Excel just because, it doesn't lend itself so much to writing paragraphs, but it's great for doing tables and calculations and graphs. And in my mind, it blows Word away in that regard. Word lends itself to basically writing the paragraphs. That's about it. I just deal with it as best I can. You can see where I have the edge of the page here, so I kind of have to watch it. I don't go over that. And you can, grab a bunch of cells and do merge and center and wrap. Um, I don't always do that. Sometimes I do it. There is a character limit in the cell. I think it's 255 characters. So if you get over that, sometimes it it just doesn't lend itself to putting a huge amount of text in one cell. Okay, so we're gonna go on with the procedure here. I'm just showing you how to do this. Like I said, I did it. I started off doing part one, and I used snip and sketch, and I took a picture of this circuit, the setup here with how to measure it, and I put it in here, and then I picked this value. Somebody mentioned the fact that these labs are too I guess, sanitary. When you do them online, they end up being exactly, you know, perfect, I guess. So I'm picking 10,067, ends up being 10.1 kiloohms. So this is the circuit I set up, and I showed you. I'm showing you the square wave and all the values that I picked. The period, and then the width of the period that ends up being the positive part, or the part that it's actually energized, and then the other part is going to be on the bottom part, and then the rise and the fall are the percentage of the slope. If you make these 0, it's going to go straight up and down, and the bigger this number, the more the slant is going to be to the actual square wave. When you do this in the lab, I'm not sure you can make all those minute changes. I think you can a little bit, but for the simplicity and consistency, I had you guys, I'm showing you what I picked on here. So what I want you to do is measure the voltage across the capacitor, and then at these different time intervals. And then at the very bottom, I want you to fill in what the time is for the voltage to be equal to 0.632. So, but if you read the theory, you would know right away what that time is going to be. So here's how to do this. This is the crux of, the importance of watching this video. So I built this thing in every circuit, and I'm going to play it. Now, here it is. That it's the voltage is going. This is what I have it set to. In this example, I changed the rise and fall to 0. My width is at 50%. My period's at 6 milliseconds. I think it has to actually be set to 1. So I'm going to click on that, and I'm going to change it to 1. And the reason it's 1 millisecond is because the frequency is 1,000 hertz. So 1 divided by 1,000, the period is 1 over the frequency. The frequency is 1 over the period. So unfortunately, in every circuit, it doesn't tell you what the frequency is. So you have to figure that out if you're asked to give a certain frequency. 1 divided by 1,000, because that's what the setup of this circuit is 1 kilohertz. So 1 divided by 1,000 is 1 millisecond. So now I'm going to reset this circuit, and I'm going to play it. It looks a little tight there. So I'm going to change this time to, let's say, 200 or maybe 100. So you can see a nice square wave there, and then you see how the capacitor charges up. So I'm going to stop it right there for a reason. That's the beginning of my scale bar on my x-axis. This is a time axis here. So you can see that at 500 milliseconds, uh, this is how long the square wave is on the 1 volt, the high part of it, and then 500 microseconds, which is 0.5 milliseconds. So the period is 1 millisecond for this whole period here. So in order to determine, the first data point is asking for 50 microseconds, right? So you have to set your time scale. I actually put my time scale on here. So I set this to 20 to get it to the first data point. And there's a reason for that. It's because I can't even find it now. I'm going to set this to 20, and then I'm going to rewind it and play it again. And I have to wait a little bit. So it started off in the high, it went low. I'm going to wait for it to go high again. And I'm going to take that point. It's just really slow now from where it was. It's going to change. Okay. So I'm going to take that when this origin point gets to my beginning of my bar. See, the bar is right there where it starts. It's a little hard to see. It's right there. I overshot it a little bit. But anyways, so they're asking you, so what? So you can see the scale isn't that great here, right? It's only showing halfway, 500 millivolts, 1 volt. So I don't like that. So I'm going to take this, which is the voltage across the source, and I'm going to turn it off. Boom. That gets much better. Okay, you can't control that on every circuit. So what I'm going to do is take a screenshot of this section. And I like to kind of cut it close to where the end of that 50 is, right? So that's going to be about right here, which I think is somewhere around 380 if I remember right. So I did all these examples, and this is the voltage across the capacitor at time shot 1. So I put time shot 1, 50 microseconds. Here's my time scale. And again, you have to kind of estimate where the end of this thing is. I drew a line at the end of the bar, which is 50 microseconds. And then here's where it started. And then I draw a line across here. And you can't really see it that well, but the 400 millivolts is about right in the center of that 400. So it's about 380. And I went likewise. I did it for time shot 2, which is 25 uh, microseconds per second. And the reason, again, that I picked that, it's kind of arbitrary, but so if you change your simulation speed, you'll notice that this bar is going to go to 100 when I go to 25. Actually, what did it before that? But I picked 25 for round, just a nice round number. So when I go to here, and then I take a shot of this, and this is where the 100 is, and that's going to be about 630. Okay, so I did it for here, and again I said it was 630, and then the time at shot 3, that was 150 microseconds is here, 200 microseconds is here, so it was 780 and 860 there. And again, this is an estimate on my part. I'm just eyeballing this. And you would have to do the same thing on a scope. It's not going to give you an exact number. You would have to, if you used an oscilloscope, you'd have to use a similar process. The only thing that's better about the scope is you actually have a grid to work with on here. It's a more well-defined grid, so it's easier to, and it's graduated. Even in between the main grid lines, there's minor grid graduations, and you would be able to pick this out a little bit easier, but I did my best. So it's green shot 3 at 150 and 200, and then 4s at 300, 400, and 500, which is down here. And as you can see, it's pretty much getting up to the steady state voltage. So that's pretty much how you do it. And then, guess what? At 100 microseconds, it's 600, 632 when you do the calculation, which is exactly one time constant. So this is showing you um, I'm sorry, this one here is showing you one time constant. So then you go on, and this is the important part of the formal lab. You have to, I'm going to save this for now. you have to go on and go through this lab and kind of, I don't want to say copy what they're saying here, but you know, say it again and rearrange the language so that you're making it flow well. So that's what I did in part F here and rewrote this with the equation and then did some calculations to show that tau for this particular circuit is 100 microseconds. And then you can calculate the capacitor from the measured tau by the measured resistance. Again, this is what I picked. You can't get exactly 10,067 ohms in every circuit, but you can get 10,100 ohms, which is what I ended up picking, which is, it's close enough. And then that shows that the capacitor was a 10 nanofarad capacitor, which is what this was. All right. And then I went on to the next part and set up another circuit with an unknown value, and I picked this value here, but just pretended I don't know what the value is. And then it's asking you the frequency of the square wave needs to be shown like this, which is basically like this. So I set this simulation speed at 500 microseconds per second, and this one at 200, so I could get a little closer, like a zoom shot, and get that value, which again, they're looking for that 63.2% value, which is one time constant. This ends up being 5 time constants, which is 2.4 milliseconds. One time constant is 474 microseconds, which the value of EC is 0.632. And then you can calculate the value of the capacitor in a similar way. And I got 47.2 nanofarads, and there it is. It's 47. It was really close. So then I skipped, and if you go and read through this, this is what it's asking you to do. And I took a screenshot of that and found out what 1 tau is, and then calculated the capacitor. And then part M says using a digital capacitance meter, if available, measure the capacitor and compare it to the value in step L. Now, we don't have one online. Obviously, we know what the capacitor is, so I just skipped that part. And then on to part 2, which I'm going to let you guys finish. I have it here, and I just started it with a header. And I'm saying student to finish the lab from here using figures, tables, graphs, and answering all questions in sentence paragraph form, including all exercises. Do not leave these notes in the report, meaning delete all this. This is just here for your edification. Report can be done in Excel or Word. Submit an appropriate submittal in Canvas. This would be AC3 submittal. And then make sure at least one of your circuits was drawn and evaluated. And I want you to do all of them in every circuit. So, and then do all the exercises at the end of the lab assignment. And then I started with figure 3.4, which is this figure here. And then you're going to have to go on and do a similar thing with the inductor, and then do a time study and find out the voltage across the resistor here, and then do some calculations. Same thing, do for this graph, there's the equation, and then answer these questions, and then do a conclusion of that part, like I did a conclusion of part 1, and then do your exercises 1, 2, 3, 4, and that's it. So good luck.